To see how to solve these equations and find the value function of a policy, it's also useful to write these equations in matrix notation. In the matrix notation, we use V pi to denote the s-dimensional vector specifying the value for every state. So V pi is effectively a vector with one entry for every state, where the little s entry is nothing but V pi of s. Similarly, R pi is the vector of rewards, the expected rewards starting from state S and following policy pi, which is nothing but s-dimensional vector with little s entry being Rs pi s. We express the transition probability matrix for policy pi as P pi, which is an S by S dimensional matrix, with S row being the distribution of the next state, if the current state is S and the action specified by policy pi is taken in that state. These definitions, it's easy to see that these equations can be expressed in compact form like this. And by moving the terms around, in fact, we can write V pi now in terms of R pi. So value function for any policy pi can be evaluated by inverting a matrix I minus gamma P pi and then multiplying it with the vector R pi. In fact, this matrix here is invertible if gamma is less than 1, and therefore it gives us a formula for finding the value vector. Let's look at our earlier example again, and let's use the formula that we just arrived to compute the value of the policy, which takes the slow action in the fallen state and the fast or the aggressive action in the other states. So we want to use the formula that V pi is equal to identity minus gamma P pi inverse R sub pi. So here V pi is the vector of all value functions. So V pi in the fallen state, V pi in the standing state, and V pi in the moving state. R pi is the vector of expected immediate rewards. We already calculated earlier the expected immediate reward of this policy in the fallen state, which was minus 0.2. For the standing state, the expected immediate reward is plus 2 with probability 0.6, because this is the probability with which the fast action, the green arrow, takes the state to the moving state. And it's minus 1 with probability 0.4, that's when it goes to the fallen state next. So the expected reward here is 0.8. For the moving state, the expected reward of taking the fast action specified by the policy is plus 2 with probability 0.8 and minus 1 with the remaining probability of 0.2, and that gives us the expected immediate reward of 1.4. So we have formed our pi vector. What remains is formulating P pi. So what's the transition probability matrix for this policy? It will be, it has 3 states, so it will be a 3 by 3 matrix. 1 row each for the fallen state, standing state, and moving state. 1 column each for fallen state, standing state, and moving state. The first row tells the distribution of the next state when you start from a fallen state and take the action specified by the policy. So in the fallen state, the policy says take slow action, which will take it to next state being fallen state with probability 0.6 and standing with probability 0.4. From the standing state, the action is fast action, which takes to fallen state with probability 0.4, no probability of remaining in standing state, and moving state with probability 0.6. From the moving state, the aggressive action takes to fallen state with probability 0.2, no probability of going to standing state, and 0.8 probability of remaining in moving state. So we have the three components of the formula, the v pi, r pi, and p pi. Now we can write down, now we can compute the value vector v pi using this formula. And I evaluated this using computer. For gamma equals 0, we know that v pi is simply going to be r pi. For gamma equals 0.9, it comes out to be close to 5.1, 7.1, 8.3. So as we expected, even the value of starting from this fallen state is non-zero, is non-negative, and in fact 5. So it makes sense to try to stand up from the fallen state. So we can evaluate one more point of gamma equals 0.1, which gives slightly less importance to future rewards than gamma equals 0.9. It's not completely myopic like gamma equals 0, but it gives less importance. In this case, actually, v pi turns out to be negative, still negative for the fallen state, which means that it still doesn't make sense to try to stand up if gamma is so small and we are not looking ahead. For other state, it's still positive. Just for exercise, let's compare it. So let's find out the value vectors of some other policy and compare it to this policy. So we can think of another simple policy, which let's say it takes slow action in all the states. So for this policy, all these terms r pi and p pi will change. So let's rewrite r pi. In the fallen state, we were taking slow action even earlier, so r pi is the same. Minus 0.2. For the standing state, the immediate reward when you take slow action is always 1. It always it's a very reliable action to take. It always goes to moving state, earns a reward 1. Similarly, in moving state, the immediate reward is always 1 for the slow action. The transition probability matrix also changes. Now in the fallen state, since we are taking the slow action again, it's the same transition probability, 0.6 of staying in fallen state, 0.4 of going to standing state. In the standing state, we are now taking the slow action, which always moves, which always transitions to the moving state. So the transition probability matrix rho is simply this. The moving state, again, taking the slow action, always keeps the process in the moving state. So the rho is this. Now if I again calculate v pi using this formula, the numbers turn out to be different. Again, for gamma equals 0, it's simply the new r pi. For gamma equals 0.9, it turns out to be 7.4, 10, and 10, which means that when we took a slow conservative action, actually for large gamma, it's better to do that. On the other hand, for small gamma, the values turned out to be this. So you see that for small gamma, the value decreased, which means it's better to take an aggressive action. So it shows you how the look ahead differentiates the policy you should take. So if you have a large gamma, meaning that you give more importance to future rewards, then you may want to use a conservative policy like using the slow action all the time. Whereas if you have small gamma, meaning that you give very much importance to the immediate rewards compared to the future rewards, then an aggressive policy like taking fast actions may be a better policy. This highlights some of the issues that we might face in terms of finding the optimal policy, and in the next lecture we will look at how to compute the optimal policy using these methods of computing the value functions of a policy.